Rob Smith here from M2 Technologies. I'm one of the simulation specialists at M2, so I normally deal with simulation mechanical, which you also see today, simulation CFD, mold flow, and the simulation modules built into Inventor itself, which is what I want to take you through in this video here. So what you're looking at currently, this is Inventor. I'm going to get back to the point where I can work a little more freely. There's some great visualization stuff built right into Inventor, including some image-based lighting environments, which you see here in the old warehouse. Some ray tracing technology, which allows us to more accurately represent shadows and textures and things like that on our models. But when it comes time to actually work, I like to turn that stuff off and go back to our default views. So what we have here is the bucket assembly for the front end loader. I'm going to turn on a what we call a level of detail. All right, so I'm going to toggle the dynamic simulation level of detail, which just allows me to suppress some extraneous parts. I don't have to delete those parts or suppress those parts and affect the design as a whole and change documentation like drawings and things like that. I can have several representations loaded in the model and quickly toggle between them. As you can see, I'm suppressing those extraneous parts, leaving only what I want to have unsuppressed for the simulations themselves. So first thing I want to show you is our dynamic simulation environment. The dynamic simulation environment is a rigid body dynamics environment, which allows us to simulate the motion of an assembly and extract from that analysis the forces, reaction forces, and loads that the parts, the assembly itself, will see under normal operating conditions. So I'm going to launch that environment right inside of Inventor here. What happens, if you look on the left side here, Inventor does a lot of the work automatically as soon as we launch into the simulation environment. It, depending on the constraints I have on the assembly, will target certain sub-assemblies and parts as grounded. Mobile groups, any unconstrained parts will be assigned to the mobile groups, where it detects that these parts, these sub-assemblies, these components are free to move as they would be in the real world, and in fact builds a series of, as you can see here, standard joints based on those constraints. So the standard joints represent points of mobility, degrees of freedom in the assembly, such as the piston assembly and any place where we've got bearings, pins, any part where the assembly in the real world is allowed to move. We get a joint where we can control degrees of freedom. We can extract information like forces, torques, and we can also apply forces, torques, and things like that at those joints. In today's analysis, what I'm going to do is apply a load onto the bucket itself, and then prescribe a motion, have that bucket lift up under that load. And what I'll do is determine first the force that's required in the hydraulic jack to lift such a load. And then in the second part of it, we'll use that information that we've extracted, plug it back into the assembly, plug that resulting load into the hydraulic jack, and see what the forces that the load on the bucket and the kinematic chain itself, see what forces those apply to the parts and the components themselves. From there, we're actually going to take those loads and throw them into another analysis, which you'll see when I get there. For now, I'm going to apply those loads. So I'll put 2 loads on, just specifying a point where the load is going to be. what direction and magnitude, so 1250 newtons. Same thing on the other side. So I've got the load on the bucket. We don't know what kind of force that the jack itself is going to have to apply to the kinematic chain in order to lift that bucket. So what we're going to use is a command called unknown force. Unknown force allows us to solve for unknown forces, things like the power that this jack is going to need. We might solve for a torque to size a motor, or size a spring. Those are the kinds of things unknown force can give us. Basically, what it's going to solve for is the force required at this joint to maintain static equilibrium in the assembly once the load and motion is applied on the bucket. So what we're looking at here is cylindrical 2, that's the name of the joint on this jack. We're going to run it through the prescribed motion. You'll see the bucket lift. And over that period of time, the duration of 1 second in this case, it's going to tell me at any point in time what force would be required at that jack to keep the bucket from moving, essentially. What we'll get from that is the maximum power that's going to be required to lift that bucket at any point in time. I'm going to hit OK here. You're going to see the process begin. See the motion is carried out. The output grapher opens up at this time. The output grapher is the star of the show in dynamic simulation. This is where we're actually extracting the good stuff that's going on at each one of these joints, at each one of these components during operation. So what you're actually looking at here in my output grapher, on the horizontal of the curve in the bottom right here, is the number of time steps, 200 time steps. The duration there was 1 second. I could show it over time as well. The curve itself is the force, the unknown force at that point in time. So with that load of, what was it, 2,500 newtons total on the bucket as it moves up through its range of motion, at any given time, the force required at the jack to maintain static equilibrium. So in order for us to actually lift the bucket, we'd have to exceed whatever that unknown force result is at that point in time. So you see the curve. You also see a tabular display of those results just above the curve. Okay, so step number and the unknown force itself. Some of the things we can do here is interrogate what the maximum value is. So right at the beginning of the analysis at step 0, we see the maximum unknown force. We can extract other information about that curve, such as the average, the minimum, standard deviation, etc. You can see on the left side in the browser, the curve we're looking at is the one we have checked, so the unknown force itself is checked. You'll see later on, when I run this again, how I can interrogate other results at different joints. For now, I'm just going to take a look at my maximum here. Again, like I said, I'm going to need to exceed this to actually lift that bucket, right? So this is the force required to keep it exactly where it is under load. If I want it to move through that load, I've got to exceed this value. So I'm going to close the output grapher for now. What I'll do is I'll go into that joint, cylindrical 2, the jack itself, and look at the properties for this joint. You see I have control over every degree of freedom. So in a cylindrical joint, I have rotation about an axis and translation along that axis. I can lock those degrees of freedom. I can apply resistance in the form of damping or stiffness. I can apply friction. Let's see, I'll set this back to the beginning position and I will add a force. Alright, so I'm going to put a joint force in here. I could have that force vary over time. Okay, you can build You could build your power curves, your load curves inside of the input grapher. That's what this is called. In this case, I'm just going to give it a constant value. Again, I want to exceed that maximum result. So rather than prescribing motion in this case, I'm actually going to input that force into the jack, watch the bucket move through its motion, and what that'll do is calculate, as a result of that input at the jack, as a result of that force, I'm going to have results at all the joints and components inside of this assembly. What's happening to the rest of the assembly when I apply that load? What I want to do to that in the end is export one of these parts, one of these components, to the stress analysis environment, and I want to use the loads that are calculated inside of this dynamic simulation. So I'm going to set that up ahead of time here. Use the export to FEA command, and I'm going to say I want this part to be exported. What it's asking me here is, okay, this part has a certain set of joints on it. When I run the analysis, those joints are going to have results at them. Where do I want to apply those results? What faces are going to see those loads when we get into the stress analysis environment? So we've got a revolution joint, the forces of which I want to apply to this face, and a welded joint on that face. Now that I've set that up, I'm going to run the analysis again with my new settings. On the simulation player, I'll hit play. I'm going to input that force. The new results can be interrogated in my output grapher now, so I'm going to go into my joints. I'm going to look at revolution 6. That's the joint that exists between the jack and the part that I am interested in. And you can see inside of the browser here I can interrogate a number of things at this spot. Relative to position, I can see velocities, accelerations, moments. In this case, I'm after a force, which when checked, you can see it applies the curve and gives me the tabular data up above. In that tabular data, I've got a checkbox, an additional checkbox here that allows me to export specific time steps to the FEA environment. So I know that my maximum here is at the end of the event. So I'm going to check 1 second. I'm going to export that time step. I'll grab a couple others. Go for 3/4 of a second and half second. And that's it, I'm done here. I'll exit the dynamic simulation environment. I can come back at any time, change things, rerun it, but for now I'm going to finish, and I'm going to load up the stress analysis environment. So, built right inside of Inventor, we have stress analysis tool that's going to allow us to run FEA analysis on linear material models, so typically ductile metals, but anything that behaves has on its stress strain curve a linear portion. Okay, so typically ductile metals, and it allows us to run stress analysis on these components, modal analysis if we're interested in the natural frequency modes, or parametric studies where we can vary things like the thickness of a stiffening rib, or change the material and run several analyses at the same time and view those results in a tabular form. So I'm going to create a simulation. Okay, so you can see we can have static analysis checked, or I can go down to modal analysis if I'm interested in a vibration study. I'm going to keep static checked, and I'm actually going to check the motion loads analysis box. Because I exported to FEA from the dynamic simulation environment, I have a list here of the parts that I've exported. Okay, so it's only the one in this case, and any time steps that I check to export. So we'll take a look at time step 1. It's going to start that simulation. Okay, so what you can see here, the parts that we're not concerned with at this time are shown in this opaque translucent form. The part itself is shown here with the loads that came across from the dynamic simulation environment. These are just glyphs indicating the loads that have come across. If you look over in the browser, you can see what did in fact come across: a couple of moments and some remote forces. I'm going to turn off the display of those just to clean up the view. Now, technically, this is ready to go. My loads and constraints are already in place from the dynamic simulation environment. I could just hit simulation now and get results. And that's perfectly valid. What it's going to do is interrogate the part and automatically mesh the part based on geometric complexity, size of the part, bounding box of the part, and run. And you know, it's in this case, you'll see, I'm going to show you in a second, the mesh is a bit coarse, but that's okay. The idea here is to run an analysis quickly during the design process just to get some quick and dirty results, to see if this idea that I have, this change I have, this design that I have is worth pursuing in more detail. So let me hit the mesh view right now and show you what the default mesh would look like for this part. Okay, so if I'd have just hit run, this is the mesh it would have used. In my opinion, a bit coarse, but like I explained, that's valid for a quick run. You might be able to eliminate certain configurations very quickly without coming back in here and tweaking some of the more advanced controls that are offered. So we have advanced control over the mesh. Not as advanced as you'll see in Simulation Mechanical, but that's by design. This is not supposed to overload the user with information. It's designed for folks who are designers and engineers, not full-time simulation analysts. So a lot of this stuff, the control is taken out of your hands. It's done in the background intentionally, and it's done well. So most of the time you don't even have to think about this stuff. You just plug in some loads and constraints, materials, and run. So if we hadn't brought loads and constraints over from the dynamic sim environment, we might use some of the commands like loads and pressures and bearings and moments, constraints like fixed constraints and pinned, and assign materials. We can override the materials in the CAD without changing the design, just to see how that would impact results, for example. This part itself would probably be actually a good candidate for thin bodies. That's where we replace solid parts with surfaces and mesh those surfaces as shell or membrane elements. That runs a lot faster than it would if you meshed it in 3D. So that's a new feature in 2013, and it's very useful. In this case, I'm gonna keep it as a solid, and I'm just gonna play with the mesh a little bit. I know the area I might be concerned with would be that small diameter surface where most of the load is going to be applied, so I might want to refine the mesh just on that area. So I'll specify a size of 5 mm on that surface, update my mesh, and you can see the preview is updated. Okay, so it wasn't just that surface. Obviously there is a growth rate applied here that I do have control over, so smaller elements were applied on that surface and they gradually grow out to larger elements where in the areas that I'm less concerned with. I have global settings as well, so if I wanted to drop down the average element size based on the bounding box of the part, I could do that. I can create curved mesh elements, so where you see faceting on the inside surfaces of these holes, particularly that big one, it'll basically put another node in the element, allowing it to bend around curved surfaces, capturing that geometry more accurately. So I'll apply those and update my mesh again. So you can see how quickly that stuff updates and how much control I really do have, which is nice. But again, you don't even have to play with that stuff. You can have global settings that you'd maybe do that once, and they would always be applied when you hit simulate. You'd never even have to touch the meshing if you don't want to. So I'm ready to run here. This is real time. Okay, it's going to run very fast. Okay, so what I see here is a displace part. It's exaggerated, and it's exaggerated intentionally, so when I do things like animate it, I can see quickly and visually where on the part most of the displacement is taking place, what direction it's displacing in. We're not looking at the displacement result contour, and what I mean by that is the colors that I see painted on the part. I'm looking at von Mises stress, so usually that's directly comparable to your yield stress, so you don't want that to exceed your yield strength of the material. It's colored on the part so that you get a quick visual feedback on where the areas of concern are. Even folks who are outside of the engineering department, lay people, I guess you could say, can quickly and easily understand with minimal guidance what areas in the part need to be addressed. You can see where the highest stress areas are here with the hottest colors very quickly. There are other results contours available as well. I can look at displacement specifically, get actual values, distance each node is displaced, safety factor, which in this case is based on the yield strength of material. If I wanted to probe a certain area, I can add probes to my display and see what the value of the result is at that particular point on the model. And several other contours are available. Stress tensors, for example. If I wanted to see just the stress in the x-axis, I can see that quickly as well.